Okay guys, a little intro for this implicit differentiation questions. There are 25 questions in this little playlist here. Basically, implicit differentiation, what do we mean when we say that? Well, here's an example of y equals a function of x, and that's explicit, isn't it? Because you clearly understand what y itself is equal to. So we say that's in explicit form. Implicit form means that we can't separate out the y's on one side and basically the function of x on the other. So they're intermixed in such a way that they cannot be manipulated so that we get y equals something. And then if it's in that form, we call it implicit. So we can't just differentiate like we would normally do and get dy dx. We have to use the rules for implicit differentiation. And here we just run along each individual term and differentiate them. But y itself, what is y? Well, y is shorthand. If you were writing this more long-windedly, you would write y of x. Y is a function of x, so you'd write it like this. This is the more long-winded way to write it. So in that respect then, y is itself a function of x. So here we've got a function of x squared. So we would need to use the function of a function rule, wouldn't we, to differentiate this. So let's run along the row in this example then and see what we do. This is first and foremost a product, isn't it, of this times that. So we have to use the product rule. So if we were differentiating then, we would write u. Now dy dx is this term differentiated. We've already said it's a function here, and it's something squared, so we use the function of a function rule to differentiate this then. So something squared, the 2 comes down, something to the 1 power less, which is power 1, which we can just leave as is, multiplied by the something differentiated. So that's u dy dx plus v, which is y squared, times du dx, and that x differentiates to 1. So there we are, that's that term differentiated. You'll notice I wrote y dashed, and often we do that to write y dashed. It's just an abbreviation of dy dx. So we've differentiated this term. Let's move along the row, differentiate the next term. X differentiates to 1 and there's 2 lots of. So that's 2. And then 3 lots of y differentiates to 3y dashed, doesn't it? And the constant at the end differentiates to 0. Now in this case, we often when we differentiate an implicit function, we generally try and simplify it and tidy it up. And if at all possible, we try and find y dashed equal to something and get it in explicit form if we can. So that's the sort of route map then when we do these problems. So that's implicit differentiation then and the methods we employ. But in this list then there's various problems that we're going to look at, and I'll just mention a couple of them if that's okay. Now first of all we're going to talk about powers. So let's have a look at powers. So if we have, for example, y equals 2 to the power x, say. Now, how would we differentiate that? Well, it's a power, isn't it? Problem with powers, we don't like this. We want everything on ground level. So typically speaking, we generally take logs. So the log of this side will equal the log of that side. Then we can invoke properties of logarithms, because this little chappy here in the power can then come down using properties of logs to x log 2. Now we've got an implicit function in this example, so we can differentiate all the way through. So log differentiates, log of something goes to 1 over something, multiplied by the something differentiated. And here we've got this many. This is just a number. If you tap it in a calculator, you'll get a fixed number. So that's that many x's differentiates to just x goes to 1, and there's this many of them, aren't there? Log 2. So it equals log 2 when you differentiate. So we get that, and then we can finish the problem off. So powers, all I was trying to say there really was we generally look to take logs to bring everything down to ground level, and then we can differentiate the implicit function that often arises. So that's powers then. Next we'll look at inverse trig functions. There's a few questions on this. So if we have arc sine, for example, and we want to find the derivative of arc sine, and we've got y equals, if we take sines both sides, so the sine of y will equal sine of the inverse sine is just the object here, because one undoes the other. Now we can differentiate, so sine differentiates to cosine, but it's a function of a function, so it goes to cos of something, multiplied by the something differentiated, and x differentiates to 1. And then we can rearrange for y dashed, can't we, and simplify. So that's generally what we do with inverse trig functions. And there's one last thing to say about equations of a tangent. So if we have a tangent, let's just draw the triangle and a gradient. So let's suppose we've got our dy dx, and we found out it has a gradient m, and then this is a general point on the straight line, xy, and this is the coordinate on the curve x1, y1. Then we know that the tan of this angle here which is the gradient of the function, is equal to the opposite height, which is y minus y1, the difference between the y's. That's the height divided by this distance here, which is the difference between the x and the x1s, x minus x1. So we can write then that y minus y1 equals, and then move this object more than one to put a bracket up to be with the m. And this is the equation we write down, the equation of a tangent, where y1 and x1 rather, so that's x1, isn't it? x1, y1 is a point on the actual curve. M is the gradient at that point, so you differentiate and get dy dx and work it out at that particular point. And then P is a general point to illustrate the straight line equation. So that's what we generally write in this example. So just touch on that. I won't do an example because there's plenty in the examples. I think from about 21 onwards, there's plenty of examples on that as well. So all the best with this section then, guys. Hope it's alright. Any feedback, of course, send me an email, and I'll catch you in the next vid. Cheers!